So I'm just going to say up front, what I'm going to argue here is purely heuristic. I'm going to write it. This is a heuristic argument. Meaning, well, in this context, what I mean is what I'm about to do does not hold up in the court of mathematics, okay? But we're just going to argue like kind of loose mathematical terms for what stress is. Who thinks stress is like a fundamental quantity? We talk about it a lot in geomechanics, right? Like, how do you measure stress? Do what?
So we measure force.
Yeah, in the laboratory, that's what you do. How's force measured in a laboratory? Inside the load cell that tells you what the force is, what's actually happening?
So you can measure the fluid
distance dx, the rate of strain, I guess.
If it's like if you're talking about like an external stress and a fluid pressure, I mean you can measure fluid pressure, okay? But let's say you're talking about an unconfined compressive strength test where you just have a sample and you're going to press on it with a load cell until it fails. How do you measure? Well, so the load cell, the instrument, has a computer readout and it tells you force. Where to get that from? Huh? Yeah, if you look inside there, if you tore it all apart and looked inside there, what you would find is either, it's really some measurement of strain. Either strain gauges, like classical strain gauges, or you can actually use piezoelectric quartz to basically measure strain. You use a piece of piezoelectric quartz to measure basically strain, and then you calibrate that to register a force, right? Like how much strain on this load cell, like how much force does that correspond to, right? And then, how do you ultimately measure force? Well, you can measure force by a weight, right? You can, by a scale, you can put a weight on something to measure force, right? So that's how you know how much force something has, okay? So you can measure fluid pressure, and that's like if you think about how we measure stress in the subsurface, it's often through like a mini frac experiment, where you produce a hydraulic fracture, and then you shut in the well and you let the hydraulic fracture close, and then at the moment of closure you say that, well, that's the equilibrium stress, therefore like the overburdened stress must be some number, right? But again, really what you're measuring is fluid pressure. So you're not, and what you're saying is that the stress, the overburden stress, is equal to the fluid pressure, right, at that moment. So you're not really, again, measuring stress in any solid material, right? So what the heck is stress then? Because I think strain is well defined, right? We just spent 3 days defining strain, right? Strain rate, and it's well defined. So what the heck is stress? And so let's start with just, whenever I don't know what to do, I just start with like physics 101, right? So let's just start with something you learned in physics. As a general rule in engineering, if you don't know what to do, start with writing down F equals ma. And that's what we're going to do next. But right now, we're going to write down that, like from physics, right? Everybody remember that an increment of work is equal to the integral of F, where F is a vector, force times distance, right? Remember, work is force times distance. Well, this is like the calculus version of that, right? you have the force vector times some direction or distance vector, okay? So what I'm going to do is I'm going to divide, so I'm not taking a time derivative, but I'm going to, instead of taking a time derivative, and again, please, like this is heuristic, right? We're just trying to loosely prove a point without like diving into rigorous mathematics. Okay, so we're going to divide both sides by dt. Okay, what's the time rate of change of work called? Power, right? So we have power on the far left, and over here, well, again that x, I'll just say x, just to be clear, x is a function of big X and t, so it's in the current configuration. And so what is dx dt? We got a name for that thing. Yep. So this is the velocity. All right. So the next thing we're going to do is we're going to multiply. Remember, in math, you can, any equation, it's legal to multiply both sides of the equation by anything, right? So I'm going to multiply both sides of the equation by 1. So on this side, I'm going to multiply by 1. It's amazing how many math tricks you can do by multiplying an equation by 1, right? So on the right-hand side, my 1 is going to have a special form, right? It's going to be dv over dv, right? Everybody agree that's 1? Okay. So now dv, you might think dv is v is a scalar, right? It's a volume. That you might think of that as like the area times dx, okay? But really, this equation wouldn't make sense because this is a vector, that's a scalar, that's a scalar, right? So really, what you have here is not just an area, but like an area vector, you might think. Or in additional notation, you might say aj dxj, right? So there's like, if j goes from 1 to 3, there's 3 directions, right, in dx. So then there's like 3 areas, right? So if you have 3 areas times directions, then you can compute a volume, right? So I'm going to make this substitution, but only in the denominator here. Okay? So if I do that, I have the integral, and now I'll just switch. So this is like fi fi vi, okay? And then I'm going to have my dv here, but for this dv in the denominator, I'm going to substitute in this thing, okay? So it goes in the denominator, and then I'm just going to put them in a special location. So here I'm going to have aj, and here I'm going to have dx. J, right? So this thing has a name, dvi dxj has a name. No. This is velocity, that's spatial coordinate, right? We have a velocity and we're taking the gradient with respect to space. No. If we took a time derivative of velocity, we have acceleration. In this case, we're taking a spatial derivative. What's it called? It's almost in the name. If you just think about it, we have a velocity and we're taking a gradient. Velocity gradient, right? So, so here we have L dV. And what do we know this thing as?
Stress.
Yeah. Like a force per unit area is a stress, okay? And that's so that we're going to call that, we're going to give it a symbol. And in this case, I'm going to use this, or I'm going to introduce this colon operator. So if you have two tensors, like stress is a tensor, and we know it's a tensor because that's two free indices, right? Second order tensor. Two free indices. So tensor, 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 tensor. Then, so this colon operator, if I have this, that is the same thing as the double contraction over the indices, right? So one more thing, the velocity gradient, you know, any matrix, right? There's a decomposition for any matrix into a symmetric and a skew symmetric or anti-symmetric part, right? So any matrix can be divided into or split into its symmetric part and its anti-symmetric part. And mathematically that is 1/2 L transpose plus L plus 1/2 L minus L transpose. So this thing right here has a name. Symmetric part of the velocity gradient is the rate of deformation, right? So this is called D, and we don't have this, we don't have a name for this yet. We're going to introduce it right now. It's called the spin. So the velocity gradient is the rate of deformation plus the spin, and the important thing to note about the spin is that it's anti-symmetric, right? So if we plug in over here D plus W, right? So integral of the stress double contraction D plus W dV. Well, one thing about, if you take any anti-symmetric tensor and you contract it with a symmetric tensor. Now we haven't imposed symmetry on this yet, but let's assume now for a second that this is symmetric. So if you take something that's anti-symmetric and you can double contract it with something that's symmetric, you'll always get 0. Okay, so sigma double contract W is the 0 tensor. Okay, so finally we have that power is equal to stress dV, d dV. Okay, so the rate of deformation is well defined, right? Because we just defined it from strain measures, essentially. Things, you know, the deformation gradient, essentially, the most fundamental deformation quantity, which is valid, right? Well defined. So deformation gradient, I mean, the rate of deformation is well defined. Power is a thermodynamic quantity, it's well defined. So this thing called stress is the thing that is power conjugate to the rate of deformation. It's the thing that if we multiply by the rate of deformation, we get power. And what you'll see is that in constitutive modeling, you remember I said there's an infinite number of stress measures? And now you probably also recognize there's an infinite number of strain rate measures. I'm sorry, I said there's an infinite number of strain measures, right? And there's also an infinite number of strain rate measures, okay? So when we do constitutive modeling in finite deformation, there's also an infinite number of stresses. But the ones that are valid are the ones that are power conjugate to their corresponding strain measure, okay? So in this case, in the current configuration, so technically this thing right here is called the Cauchy stress, and it lives in the current configuration. And what the Cauchy stress is, and again, we'll see it geometrically defined, in the next, this is what we're going to do on the next, okay? But what it is it's it relates forces in, because we have two configurations, right? So the Cauchy stress relates forces in the current configuration to areas in the current configuration, okay? But what we'll see later is there are other valid stress measures, namely the first Piola-Kirchhoff stress and the second Piola-Kirchhoff stress. And what they do is relate forces in the reference configuration to to areas in the reference configuration, and forces in the current configuration to areas in the reference configuration. So it's just something to be aware of, is that you have to use a thermodynamically consistent stress for whatever strain or strain rate you're using. Yeah. So just something to think about what stress is.